Hello everyone, I'm Alex, the account manager of Moldex3d EMEA team. So first of all, I would like to thank you for joining this webinar today. And today I'm gonna to have a presentation about improving structural performance of fiber reinforced plastic parts. So this topic is quite heated up in recent years, especially for customers who are interested how to fill the gap between structure simulation and the reality by having a consideration of molding process, how this process would affect the strength of your product. So make story short, let's take a look about the outline today. In the beginning, I would like to quickly introduce why Moldex3d. So the theory behind the software and how accurate it could be in terms of a prediction of fiber orientation. And second, I would introduce what Moldex3d could output for further structure analysis. The last but not the least, I will also share two real case studies from our customers who joined the Global Innovation Talent Contest last year, which perfectly showed how they use Moldex3d as a basis to further perform the structural analysis in order to improve their product. So start from the beginning. I think it is quite well known that fiber reinforced plastic parts has widely acted as a major material for lots of plastic parts in different industries. So because it has the advantages of high strength to weight ratio, high toughness to anti-corrosion, and high creep resistance. So however, fiber reinforced plastics has versatile mechanical characteristics due to different fibers, matrix, and the manufacturing process. As the picture has been shown here, the fiber strength could be different from short fiber to long fiber, even matte or fabric type. And the process will also be different from traditional injection molding to compression molding, such as SMC and GMT and even RTM. And above mentioned process can also be simulated in Moldex3d. And because of the difference of fiber orientation and the length, their deformation, fracture, and ultimate strength owing to external loads are hard to predict, but very crucial for all the CA engineer. So let's take a look about our fiber prediction model. So in 2013, Moldex3d proposed the 3-parameter IARD RPR models in US patent. So where the IARD model it stands for is the improvement of the IARD model, which describes rotary diffusion, includes two parameters, CI and CN. CI is the fiber-to-fiber interaction parameter, and CN is the fiber-to-matrix interaction. And about the RPR model, is indicative of retarding principal rate to slow down the fast transient orientation rate by parameter alpha. In general, this model involves three terms. First is the Jeffrey hydrodynamics, as you can see on the bottom picture, and also the rotary diffusion and the fiber matrix interaction. So including these three phenomena, which is very suitable for the predicting the core shear orientation structure inside the simulation. And let's take a look about the how is the most advantage in our material model what we can provide to our customer. So the first thing is that I think by using this fiber model, we can provide quite highest accurate fiber orientation prediction. So which we will take a look about some validation later on. And second is about there only includes 3 parameters, which has their own physical meaning. So unlike other software, some other software they have even 5 or 6 parameters, which don't include any physical meaning. It means that in this case, you might just make a try and error to tune each parameter and try to fit in with your simulation between experimental data, which is quite, I would say, tedious job. And third is about the boundary condition in the inlet. So there is no need to specify the inlet orientation condition. Basically, this is also quite big advantage, because in other software, some user they need to specify specific orientation to fill the gap between the simulation result and the reality. And since we have this fiber model in 2013, so in 2014 to 2016, Moldex3d has been invited to join the US Department of Energy program. And this program is led by Oak Ridge National Laboratory, which also consists of 2 academic units, Illinois and the Virginia Technology University. So also BASF and Ford are in this project. So you can imagine this is a very sizable project. So the goal of this project is to find a suitable engineering tool for predicting long carbon fiber of thermoplastic materials. So since we joined this program, so there are some validation. So in the phase 1, this is the product which has been used as a test to check whether our software is reliable. Yeah. So as you can see, this is quite a simple product with a long plate and in a different area. So in this program, they find in different 3 space position and to check whether the fiber orientation from the CT scan can perfectly fit in with our simulation result. So since we passed this phase, so there are the second phase. There's another challenge to check our software. So this is the product. What we have in the second phase is a seat back, which we can see in the daily life in our car. So this is a quite I would say familiar part. And the challenge is that they try to measure, as you can see, in different position, especially in the position where you have the direction change as the red circle area. So in this rib area and also in some the change in the thickness area, this is a quite typical position that the customer they want to have a deeper look about the fiber orientation prediction. So this is the result in the end. So after checking the simulation result with the experimental data and also compare with the Morphlow, so the criteria is that if there is 15% difference in comparison with the simulation and the experimental, so which means this result is out. So as you can see, in Moldex3d, the fiber prediction, they are 8 of 9, which passed the test, which also shows us that this is a quite very successful story for us to prove that our fiber orientation prediction is very accurate in terms of other software. And even we got this quite a good successful story, we're still trying to improve our fiber model. So this is something that we keep developing the new solver, the enhanced fiber solver, to improve our fiber prediction result, which we call the fiber coupling. So as you can see, in the past, we calculate the the flow field first, then we get the fiber orientation in the end of feeding. But the truth is that during the feeding, the orientation should be a transient process. So in the fiber coupling solver, what we include is that we will have a more iteration during the feeding calculation. So once we get the flow field, we will calculate the orientation, and this orientation will be taken into account how it affects the viscosity and the further stress, and have a final response to the flow behavior. So which means that this is the biggest difference in comparison with the conventional fiber solver and the enhanced fiber solver, which one is coupled and one is decoupled. And the reason we developed this solver is that, as you can see, this is some experimental observation. We found that in a long plate with a high percentage of short fiber or even long fiber, as you can see from the beginning to the end, the shape will be from the convex contour and plug flow, and finally concave contour. But in our simulation, this is something that we cannot predict well. And also in certain process like SMC with a strongly aligned fiber orientation in specified axis. For example, on the right hand side, the fiber orientation in the very beginning is aligned with the x-axis. But the truth is that the male front should have a non-uniform male front. But by using the conventional solver, what we get, the result is that the simulation will have a perfectly circular shape during the compression. So this is something that after we consider the enhanced fiber solver, so what we can see is that this male front can be perfectly predicted as what we found in the experimental data in terms of long fiber, as we can see on the right hand side. And also for the compression molding like GMT and SMC, and what we can also reproduce is that by using this enhanced solver, so we can get a non-symmetry flow behavior during compression, which affects by the specific fiber axis orientation in the very beginning. So this is something that we are trying to make this enhanced solver, and because we never compromise the accuracy between simulation in comparison with the reality. So this is something that what we have, and also you can find only in Moldex3d, the enhanced fiber solver, consider the coupling fiber simulation in terms of the influence between fiber orientation and the flow behavior. And after realizing that why we choose Moldex3d as a reliable tool for the fiber prediction, so then we can further take a look about more detail about today's topic, which is the connection between Moldex3d and the structural analysis. So when it comes to structural analysis, there are several factors which should be taken into account, like the geometry of the part itself, also the boundary conditions such as where should be fixed, and the axis might have a possibility to move in some different freedom in the different position, and how and where the force will be applied. And all of this can be easily set up in the normal CAE software, except material, because without the consideration of how process affect the FRP, then it can only be considered as isotropic material. So this is quite the commonly used material model when we try to do the simulation. If the material is without fiber, so we can assume it's isotropic. So this is probably the most commonly used one for the most structural analysis. And once the fiber has been included, the orientation of the fiber will strongly affect the strength of the part in terms of the flow direction and the transverse direction. For more advanced analysis, so it might also consider the nonlinear material model, so from basic linear elastic to elastoplastic model. And let's take a look about how much the difference between isotropic and isotropic and anisotropic with nonlinear. So let's take on the top, both of the picture. On the left one, it shows that the isotropic nonlinear, but on the right hand side, it shows anisotropic nonlinear. So what we can find is that if we consider the material as isotropic, there's only one stress-strain curve. But the truth is that in the reality, the fiber orientation, it makes a big influence in terms of the strength curve. I would say the product strength due to the fiber orientation. So as we can see on the right hand side, in the different direction of the fiber from 0 degree to 90 degree. So the stress-strain curve shows totally abuse different behavior in comparison with the isotropic material. And if we take a further look to compare the anisotropic linear and the anisotropic nonlinear, so what we can also imagine is that if we will only consider the material is linear, so which means it doesn't take into account about the material over the certain stress maxima, which will start to going down with a flat curve, as we can see in the nonlinear curve. So this is also quite crucial for the customer when they want to make a more accurate structural simulation, because the material model, it really matters how the result it could be. And now this slide is showing that what do we have, what we can provide to the customer to have a better structural simulation result. So first, for the normal user, if they don't have any structural software, they can just use Moldex3d stress solver to do the very basic simulation to make some fixed boundary and some force the loading on a certain area to make some static structural simulation. But for the customer who is more who already have a FES software in-house, so like ANSYS or Abacus, so they can consider to output our fiber orientation as a basis to further run the simulation in the FIA software, what they used to do. And for a more advanced user, if they want to do some kind of a more advanced simulation, like if it involves the big deformation during the structural simulation, so the nonlinear material property is also a must tool which should be considered during the structural analysis. So in this case, we will involve DGMAT RP. And this is a quite a clear picture showing that for different user and which kind of tool we can provide for the different structure CAE engineer. So like what I say, on if the user is very entry level, so Moldex3d stress solver is definitely a good choice for you. But if you already have some similar experience about the in-house software like ANSYS or Abacus, even LS Dyna, so you can consider output the FIA interface, the result, the fiber orientation from FIA interface to your company use FIA software for further investigation. But if it involves like nonlinear behaviors like failure, buckling, large deformation, crack, or fatigue. So in this case, I think to use DGMAT RP, it would be a very good solution for you to consider a nonlinear material model. And this is the user interface, how it looks like when we consider to output the VI interface. So the workflow is quite simple. So there are 4 different steps. So first you choose which one is the software, the type you want to output from ANSYS, Abacus, or Elastina, even Nastran, Workbench, something like this. And the second one is quite also important. So if I using the BLM, so you can choose to output the original mesh. But sometimes the customer might have some question because the mesh we prepare in our software has too much element compared with the normal structural analysis what they prepare for. So there is also a very important function which we call the mapping. So we can also map the mesh, the material model from the original Moldex3d mesh to further the mesh prepared by the structure simulation software. And the third is that, as you can see, we have many things for output. If you want to do the thermal simulation, you can also consider output the temperature. And if you are mainly concerned about the anisotropic material behavior, so you can directly output the fiber orientation. And there's also one thing worth mentioned, because sometimes even using the mapping function, the material model is still too much in consideration of the memory usage when we do the structural simulation. So there's a function which, as we can see here, the material reduction of fiber orientation. So in this case, for your reference, you might also consider choosing high level reduction to tremendously reduce the material model, which can help you have a better memory usage during the structural simulation calculation. And the fourth step is just to export this input data. Okay, so yeah, as you can see, this is the workflow from Moldex3d to VI interface. And after we output the data from VI interface, we can directly run the finite element simulation in your company use structured software. And the item we can output is the basic, like the stress and also the welding line, how it affects the strength and the fiber orientation. And furthermore, also some mode-based temperature and the mode-based pressure can also be considered. And let's take a look about the benefits of Moldex3d Digimat RP. So the best thing to use Digimat RP is that it includes many kinds of material models. So from elastic, elastoplastic, thermoelastic, thermoelastoplastic. So they are all available in the Digimat RP. And there's also one very important thing is that, so by using Digimat RP, it includes around 132 material model already in the Digimat NX material database, which user can easily choose what they are commonly used for the simulation. And furthermore, if they cannot find the material in the database, they can also consider by creating their own material model, which we would say this is kind of a reverse engineering. So in the beginning, you can input the experimental data provided from the material supplier or your own material laboratory. So in this case, you can just create the straight strain curve in different direction of your sample test from 0 degree, 45 degree, and 90 degree. And by providing this kind of straight strain curve, so the Digimat RP can do the reverse engineering to create the material model for what you really use for the process. So I would say this is kind of a customized function. And also in the Digimat RP, this is also something quite important for the user, because all the workflow is quite friendly and easy to use. So this is the procedure how to use the Digimate RP. So first we import the VI model from the structure software, and secondly we import the material model. Like what I say, you can choose from the embedded in material database in Digimate RP, or you can also create your material model by input the experimental data like stress strain curve to do the reverse engineering. And thirdly, you can specify fiber orientation, which this result will be read from what we output from the VI interface, like what we showed in few slides before. And the fourth step, so Digimate can also do the mapping from the fiber orientation from the Moldex3d mesh to the VI model. And finally, you just submit a job and you can check the result in your VI software. So I think the workflow is quite simple and easy to use. And now the first case study I would like to share with you is a case from our customer in Taiwan, Pegatron. Pegatron is one of the biggest OEM company who produce computer, consumer electronic, communication, and car electronic products. So one of the well-known product I think you must know is a product from Apple, iPad. So, but today the part I will use is a button-based case cover of tablet. So since we are talking about the tablet, so you can imagine that the tablet we use now is getting lighter and thinner day by day. So in the industry, they are also facing the difficulty to keep the same thermal dissipation effect but less thickness. This is a quite challengeable job. In original design, the thickness of part is with 1.1 thickness and also on the top with some high thermal conductivity material. And however, the new design will be embedded with the 0.5 mm metal insert and the total 1.0 thickness as picture shown on the right hand side. So you can find that around 70% of the part will be very thin, equal to 0.5 mm. So which is very difficult to be molded. And how the design can be successfully molded is the first challenge. So in the original story, they overcome the show shot effect and improve the pressure drop and the final warpage. But this is not today's main topics. We should focus on more in the second challenge, which is how the part strength can be validated. So yeah, this is some product introduction, and the length, the width, and the height is 273, 160, and 4.5 millimeters separately. And thickness is like what I mentioned, around 0.5 to 1 millimeters. And the mesh we use is a boundary layer mesh with 5 layers. So the total will be 11 layers around thickness. And the mesh count is around 1.6 million. So this is the material we used. For the plastic part is polycarbonate, and for the metal insert is aluminum. And this is the final material that has been selected after few different trials. The material is from Subic, polycarbonate with 40% glass fiber, also with high fluidity around 40 mFi. And this is a mill front result. So as you can see, this is a 3-plate plus metal insert mold. Runner is a combination with the hard runner and the cold runner. And on the left bottom corner, you can also find the ISO contour of the mill front. Once we have the mill front behavior, we can further get the fiber orientation along different direction. So as you can see, the higher the value, it means that the fiber is more oriented along the given direction. So for example, if the result of the fiber orientation along x direction is higher, so it's around the 0.8, so we can understand this. The fiber orientation is highly aligned with the x direction as we see here, because in the coordinates it shows here is x and y. Also on the opposite, we can find for the fiber orientation along y direction on the two sides, it also shows high fiber orientation along y direction, as we can see from the color it stands for. Okay, so after having the result of the fiber orientation, so what's the next step is that we output our fiber orientation to the FIA by using the FIA interface to the FIA software. And the FIA software they use here is the ANSYS. Okay, and they did two different strength validation. They give two different kind of boundary condition. The first one is with a pressure loading in the middle and the fixed boundary around the corner of the back cover. And secondly, they have a clamp the two short span edges of the back cover and rotated each edge with 5 degrees. And this is the sound simulation result as we can see. And as what I say, originally they have a different design. So what you can find here is the one on the right bottom side. Here it shows the final design with the material including the highest percentage with the glass fiber. But the original design is that all of the part is plastic without any metal insert. And the second one is with an insert but without any fiber including inside the material. And the third model is that the polycarbonate plus 10% glass fiber. So this is the difference showing that in each design how the total deformation by applying the pressure loading in the middle. So as we can see in the final design, it has the lowest deformation, which means that the strength of the part has been highly improved. And also for the second test with the twist on two sides. So what we can find is that in different designs, the deformation could be different. And for the optimized design, we can get the lowest total deformation, as we can see on the right bottom corner. So in summary, what we can see is that by using the CAE software, we can gradually validate different design in different phases to find out which one is the best, the most improved one in terms of the strength validation. So as we can see in the final design, the optimized design, we will have a overall 68% improvement in comparison with the original design, which is a very big improvement. And secondly, in the twist test, I think the improvement is not that big, but it also provides us quite, from the quality point of view, we can find the good direction to improve our product in terms of a strength test by using the CAE software to do the validation, especially in consideration with the fiber orientation, the output from the FIA interface to the FIA software. And the second case study I would like to share is from the company, the Stanley Black & Decker. So I would say this company is a well-known American manufacturer of industry tools and household hardware. So the model they simulate is a part from Stanley Bostage and fastening tool, stapler, or hammer taker. So in this model, what they want to test is that in the past, they didn't consider the anisotropic behavior of the material model. So what they want to do is that to see how much the difference it could be by considering isotropic material and anisotropic material. And this is a product what we will use for the simulation. Later on, you will see the result. It's the left housing and the right housing, two different parts. And this is the rounder system design. So with a quite simple rounder system and with a rectangular gate equal to 2 times 6.8 millimeters. How the size it looks like. And this is the material has been used in this simulation, polyamide 66 with a 30% carbon fiber. And this is the melt from time result. So since we get the melt from time result, we can further check about the fiber orientation. And this is the result showing that the fiber orientation along the x direction. And at the red circle area, so in this area, as you can see, originally will be subjected with the maximum stress because according to what they found by doing the structural simulation without considering the anisotropic material behavior. And now what we can do is that we will consider this output from Moldex3d, the fiber orientation. As you can see, along the x direction, the fiber is quite highly oriented along this direction, so it might have a big influence in terms of the strength validation. So what they do is that, as a matter of fact, they don't have the in the via interface function, they cannot select the radial stress over here. So they alternatively they choose the abstract as output because the file type can be also tolerated between both software. And secondly, they choose the fiber orientation tensor as output, which is the O2D file, as you can see on the right hand side, and the FEM file means that the Moldex3d mesh. And in order to mimic the way we use this tool, so what they have done is that they set up the BC with a 25 feet per second with an angular velocity and also a rotation center, as you can see, as a reference coordination. And this is a stress result during the simulation. So what we can find is that the stress distribution could be quite different in comparison with the result without considering fiber orientation and the result with the considering fiber orientation, also the concentration area. And if we take deeper look about the value, as we can see the area, here we choose the point as 2662438. This is the number of the node what we choose, and we take a deeper look about how the stress distribution during the dynamic simulation. So we can find that there's a amazing fact that when we consider fiber orientation, the stress value, the response could be quite high in comparison with the one which we don't consider the fiber orientation. So this is something quite important for the engineer to consider for further, I would say, strength improvement in this product. And if we also check about the stress concentration, we can also find a little bit difference between two simulation, but they are not too much difference. And so this is the strain result between two simulation, which the first one is without fiber orientation and the second one is with fiber orientation. So we could see the different structural deformation behavior, so in comparison with the isotropic and anisotropic material property. So I think as long as we are trying to reduce the weight but keeping or enhance the strength of the part, the way of taking into fiber orientation account for structural simulation would be very crucial. And for engineer to validate the strength of the part by simulation is also very important. So I would say from quality and quantity point of view, an isotropic material would bring a lot of influence, unlike what we used to do by using anisotropic material as a basis. So I think that's the that's the reason why we must use Moldex3d to help us improve the product, and for sure to have a better life, and to also reduce the daily job for all the CN engineer. So this is this is my presentation today. So thanks for your time to join the webinar. I hope you enjoyed these topics. So if you have any question, please feel free to mention it.